Good morning, everyone. My name is David Denton. I'm going to talk to you today about servers and function in Kotlin. There's a second name on there, Ivan Sanchez. He is my cohort in everything we've done. So I always, we all he's given this talk, I've given it, and we always credit each other. So he's half to blame, as it were, for everything. So what is this about? So this is kind of a journey story, really, about how we took a scientific publishing website, which we were developing, and we, when we remodeled it, it was originally in Java and Scala. We remodeled it, and along the way, we applied this pattern, which is server as a function, which I'll tell you about in a moment. And we end up writing an open source HTTP library into the mix. So, right, so let's get started. Okay. So I suppose the starting point of this is the Oscar platform. Now, the Oscar platform was a scientific publisher website for a big academic publisher. They basically provide scientific publishing on the web, as it were. So you can download articles and papers and PDFs and that kind of thing. Originally, it was written in Java and Scala, and it's one of the top 1,000 sites globally. About a few tens of millions of hits a day. So it turns out when after you get past the big first few, there's a real big drop off. But so it's not, although it's top 1,000, it's not that much traffic really. But how is it structured? It's structured as a monorepo. We host it in GitHub. We continuously build and deploy using GoCD, which is the ThoughtWorks continuous deployment platform, and we're deploying it to Cloud Foundry. So one thing to note about the Java Oscar platform was that it was written in quite an unusual style. So the style was very functional. Before Java introduced their functional libraries, we were using another different library called Totally Lazy, which was an open source, which kind of gave you the functional constructs that you'll probably be used to seeing in modern Java and languages like Scala and now Kotlin. So what we decided to do was, they started about 2015 or so. They decided to say, well, let's see if we can actually start to leverage Kotlin. It's a new language. It's kind of next generation Java. Let's see what we can do. Just actually, by show of hands, who has heard of Kotlin? Good. And does everyone know what it is if they haven't heard of it? Good. Does anyone not know what it is? Okay, fine. Anyway, right. Okay, so we were delivering basically, we were using heavy XP practices, lots of testing. That's very important. Yes, so we'll get into exactly how it was. Now, around the time we decided to start leveraging Kotlin for this platform, we kind of had what we call a Techrospective, which is kind of retrospective, but just purely based upon the technology rather than process and stuff that you might find in a retrospective. And we came up with a few things that we had issues with. So we were using at the time an HTTP library called Utterly Idle, which kind of played really well with this function library we're using. That was also open source. But we found that we had some issues. And one of the issues was we were using a mutable HTTP model. Now, in the days, we actually personally favored immutability, because immutability means it's safer, and et cetera, et cetera. So it kind of bugged us. We were using a mutable HTTP model under the covers. And what it meant is, as you were kind of stepping through the code, the request and response objects could change underneath you, so you couldn't see exactly at any point in the code what the values of various things were, because they could change. That meant it was hard to debug. We had a load of boilerplate around application setup. So we had like a dependency injection framework that kind of came with Utterly Idle, which it was Spring-esque, I suppose. So there's kind of loads of reflection, loads of magic going on. Once again, it was kind of we found it hard to debug. And if things went wrong, it was kind of like it's sad face time, as it were. Also, there was magic around routing, so HTTP routing. So if you think about paths, and it was taking, what I would do with that was actually kind of extract out bits of the request, like queries and headers and stuff, and actually put them into a Typesafe kind of model, and then inject them into your kind of handler functions. So that was good, but we wanted to retain that type safety, but we didn't like the fact that the routing was really also hard to debug. We found it really hard to test end-to-end services because of the way we couldn't spin up everything in memory. We had to open network ports and stuff, which limits the ability to parallelize your tests. So it was kind of difficult and kind of slow to actually to test things. And also there was, as we started to put things into Kotlin, Kotlin comes with its own functional constructs built in. And so what we were getting was kind of some aggravation between the two APIs, because you call a map function, and there's two maps. There's a map on the Kotlin list, and there's also a map on the functional list as well. So what do? We said, let's try something simple. Let's see if we can start again and actually just start with the bare bones and see where we can get to. It was just with using Kotlin. So the first attempt at this was done on a hack day. Ivan, my cohort, and another guy got into a room, and they basically saw how much. They were saying, how much can we do in one day, and how much can we replace of this magic framework that we've got? And it turns out that in 40 lines of Kotlin code, they managed to pretty much bang together a almost full HTTP framework for routing and kind of taking requests and putting to handlers. So that was great, and that we thought, well, this is really something we can actually take forward, and let's see how far we can do. You can see the code. There's a bit.ly link there with the code. It's quite tied to the utterly idle model, the framework we were using, but it kind of gives you an idea about what we were trying to achieve. And if there's one thing we want to take away from this thing, is that this talk is, don't be afraid to try this kind of thing. If something is hard or something you're finding, really look and see if you can boil down problems, and kind of by taking a step back, you may be able to actually really kind of come up with something that will make your lives a lot easier. So, server as a function, what is it? So in 2014, a guy at Twitter, Marius Eriksson, or was it 2013, sorry, wrote a white paper with your server as a function. And that paper said, well, you can model distributed services, distributed microservices, as it were, as two basic concepts. One of those concepts is called the other one's called a filter. Now, what are they? So a service is just a thing, it's just a function that takes a request and turns it into a response. It's a system boundary. So the actual model from the paper was an asynchronous response, so it was taking a request and turning it into a future response. And so that's basically your handler, basically. And the filter is also called a middleware in other frameworks you might be useful to. It basically applies pre and post processing to a request or response. So you can take a request and you can rewrite the URL, or you can take a response and set some headers and that kind of thing. So it applies IO transforms. So the idea behind filters is that you can inject kind of cross-cutting concerns like logging and metrics and that kind of stuff, and it's all nicely segregated from your actual code that's doing your business logic. Twitter themselves, they have a Scala implementation of server as a function. Their library is called Finagle. We used it for a couple of years. Finagle is it's written in Scala, it's written on Netty, and the thing about it is it's protocol agnostic, which basically what it means is it doesn't just do HTTP, it does all other protocols or any that you wish to do. Because of the genericness of the function signatures, you can do Thrift, you can do SQL, you can do any protocol you want, basically. As long as it's kind of got this request response kind of model, you can do that. We found, however, the future-based stuff, asynchronicity, adds complexity. So that was a thing that really started to bite, and people didn't really understand it, and it was difficult to debug, once again. So there was kind of a bit of friction there. So that's, we were using Finagle, but we actually decided we actually want to move towards a kind of Kotlin-based platform. So why did we choose Kotlin? So we chose Kotlin because it's Java done right. Kotlin was kind of created by JetBrains, the tooling company. I presume that pretty much most people who are doing Java use JetBrains tools now. IntelliJ is kind of the de facto platform for developing. They also, with the Android Studio was ported over to become an IntelliJ-based platform, which that really helped to kind of get JetBrains stuff going. It's got total interoperability with Java. which is great because you can mix and match Kotlin and Java code together. They can coexist, and you can add Kotlin support to your libraries or your applications by just like 2 lines in a Gradle file, and that's it. And then you can start to use it. It also comes with a load of annotations that allow you to call Java functions from Kotlin. Well, call Kotlin functions from Java because of the way that Kotlin has a superior type system. Not everything is callable directly by Java, so there's real help to be JetBrains have really concentrated on nailing that interoperability and easing the developer experience. They also do multi-platform as well, so not just native, but I mean obviously they've got Android. There's also Kotlin will also compile to JavaScript, and they're also working on native stuff, so you can run it on your light switches, or and also iOS is kind of early days as well. So that stuff is coming. So it's quite an exciting time because JetBrains are obviously pushing really hard, and they're really listening to the community, and it's pretty good. The other thing is that Kotlin is the most it's the highest GitHub contributor improvement over the last 12 months. So it's 2.6. So it was right at the top of that table. Okay. So what does it look like? Okay, so so here's a bit of Java. Okay, this is a fairly standard kind of, I suppose, decent Java class. It's got some function, it's got some fields, it's got some getters. If we scroll down, it's got a couple of constructors, and then it's got only one method. They've got 2 methods. Is destroyed. This is a ship. It doesn't really matter what the code does. It's just like this is what kind of standard immutable Kotlin Java looks like, and we've got equals hashcode and toString. Okay, so in Kotlin, that's the same thing. So that's 80 lines of code, over 80 lines of code, down to basically 4. So that's the same kind of productivity kind of improvement and actually compactness that you're getting kind of from Scala. It's very, very similar to Scala. If you actually looked at that and you could change the word data to case, and pretty much that you would have Scala. So it's basically stolen a lot of the ideas from the various other languages. So you've got inline constructors, you've got vals, which is immutable by default. There's val and var, but Kotlin favors immutability by default. Instead of get and setters, we have property-based stuff, and there's also stuff like default parameters as well, which removes the need to have overloaded constructors. And the word kind of public is missing as well because it's public by default. So all the kind of cruft that you would be used to in Java has kind of been stripped away. And this goes kind of for the APIs as well. The APIs are much more pleasant to use than generally in Java. So remember, in Java, I think you still can't read a line. You can't read a file of a text file to a string in one line of code. You still have to use a library. In Kotlin, you can do it. There's like a file.readText. It's just those kind of levels of kind of developer niceness means you have less to lean on other kind of libraries. So generally, everything's quite lightweight, which is nice. So server as a function distilled. So what did we do? How did we apply server as a function to our project? So we started thinking about it. We saw the pattern. We'd used it in Scala, and we thought, okay, we want to try this, and what can we do? So we thought we can improve what we've got. Let's leverage Kotlin, so it's purely Kotlin, and let's try to make it as type-safe as possible. So we came up with HttpHandler. Eventually, this is HttpHandler is like a really lightweight, zero dependencies Kotlin web library. It's kind of, is it a framework? Is it a library? I suppose you could probably say it's a framework now. I like to think of it as a library because it hasn't got dependencies, and it doesn't really enforce on you that kind of framework. Kind of brings in kind of bad connotations, as it were. So in my mind, we like to think of it as a library. So it's really lightweight. It has zero dependencies. It's about 800K, the core library. It provides a full server and client implementation in that space because it's really leveraging what's already in the JDK. There's zero magic. There's no annotations. There's no reflection, which means basically it's fast. So how does it look? Okay, so from server as a function, we took the service concept and we said, well, we're only interested in HTTP. So we renamed the service to HttpHandler. So what does it do? Well, an HTTP handler is just a function, and actually it's a function. It's a type alias, which in Kotlin it's not even an interface. So it's literally just an alias for something that takes a function that takes a request and turns it into a response. That's the Kotlin. That's the Kotlin type signature. It really is just that. What does it look like? Okay, so in Kotlin here, we've got this is an echo HTTP handler. So what it does is it basically takes the body from a request and it bounces it into response and returns it. So that's it's fairly similar to what Java looks like. You'll notice that we haven't actually had to declare an interface or a construction because it's just a function. One thing here, and you can see actually we want to call that function. If we want to actually invoke it, how do we invoke a function? We just literally pass it a request. That's all we do. So all this is offline. We create a request here with a body, and we pass it into the function, and we get back a response. So that is it. There's no network. There's nothing. It's just request response. That's it. What's actually not shown on here, but is worth noting, is that the HTTP message request and response model is completely immutable as well. So it leverages data classes. Although we do support streaming behind the covers, as far as developers concerned, everything's immutable, and that makes it really easy to test. So that was the HTTP handler. So the other concept that we had was a filter. So a filter applies some pre- and post-processing to a request or response. And actually, when you boil down the interface, what you actually get is just it decorates an HTTP handler with some more information, some more functionality. It's just a function, so it takes an HTTP handler and it returns an HTTP handler. This one is modeled interface, but it's only got one method on it. So how does that look? Okay, so this is a Twitter filter. There's a Twitter theme going through the entire thing because I thought we should probably nod to them, considering we stole the idea from them. So it's only pleasant. So a filter here, you can basically say filter takes a handler. And so what does this one do? This basically strips 140 characters from the request body and puts it in a response and returns it. So you can see basically it doesn't return it. Actually, what it does is actually it passes it on to the next in the chain. So a filter, what this is doing effectively is applying a chain. So you can put filters on top of each other. So you can see here, you can say Twitter filter, then echo. So what this is it's modifying the echo functionality. So what this will do is basically it'll only pass through the first 140 characters to the next filter in the chain. So that's, once again, it's just a function. That's all there is to it. And the nice thing about functions is they compose. So if you compose, you can compose different filters together. So you can do filter A and filter B, you get another filter back, which is exactly the same thing. And then at the end, you get a chain, and you apply it to an HTTP handler, and you get an HTTP handler. So that allows us to serve some HTTP traffic, but we don't always want to serve the same request, the same type of response. So what we need to do is be able to say, well, for this URL, go and do this. For this URL, go and do that. So we need a routing capability. So we came up with a new concept, which is router. And once again, all it does is match an HTTP handler against a request, basically. So in Kotlin, you see this question mark, which is basically, this is a nullable type. So Kotlin models nullability inside the type system. So this means that null pointers are effectively should be almost impossible to get if you use the cat language correctly. Which is, if you look on Stack Overflow, the biggest cause of Java problems are null pointer exceptions. So literally, this entire class of problems have just been removed from the language by modeling nullability inside the type system. And so if you try and assign something that is null to something that cannot be null, you get a compile exception. So it won't even compile. Okay, anyway, back to this. Anyway, so this is the router. So router takes request and returns a handler. So basically what it does is you can do what you like, but this one, for instance, it matches the URL pattern. So you can compose multiple routers together into this kind of a tree structure. This is kind of fairly similar to quite a lot of different HTTP libraries. We're basically taking a path and we're binding an HTTP verb to an HTTP handler, and what we're getting back is another HTTP handler. So that's like just all it's doing is just basically providing that routing capability. So once again, that's it. It's just Once again, it's just a function. These things, and at the end, if you can't actually get anything out of this, it will basically fall back to a 404. That's kind of the behaviour there. So with those building blocks, we've actually got what should be the ability to serve any kind of web API as required. I mean, it hasn't got any metrics or any of that good stuff you might need to operate it, but that's kind of the bare bones of what you could actually do with an HTTP library. So if we want to, but unless we can put that function onto a network, it's no use. So what we've got, what we can do is actually take an HTTP handler and actually put it into a container. So here's our handler again, and basically if we want to turn it into a server, there's a function here called asServer, which is an extension function, which is another thing from Kotlin. Allows you to basically extend any class with or type with more functionality. And here we're taking that and putting it into an undertow server and starting it up. So basically, these are the backends we support. We support Jetty, Undertow. There's a Sun HTTP server, which is actually built into the JDK, so you get that completely for free. There's Netty, you can't really want to read the Netty, but and there's Apache HTTP as well. So all of those, if you wanted to swap it out, all would happen is you could basically take the word Undertow there and just trade it for Jetty or Sun HTTP or whatever, and that will change the server implementation. And you can obviously, you can customize, and there are APIs for actually customizing the implementation, but generally speaking, this is as simple as you can make it, and it will work. So consuming HTTP. So this is where server as a function really kind of starts to show its power, in that if I just, as well as serving a request, I might actually want to talk to another external system. And if it's over HTTP, then I'm going to actually have to make a call to it. And so we can actually reuse the same type alias that we'd already defined, which is HttpHandler. So the input and the output type aliases, the input and output signatures for incoming traffic and outgoing traffic are exactly the same, which is interesting because, this is, once again, it's taking a request and returns a response. That is the redeclaration of the same thing. So if we want to make a handler, a client, this one's an Apache one, we can just do Apache client and then we pass it a request because it's just a function. It's exactly the same interface. And so we support Apache, Jetty, OKHTTP, and then the Sun one, which is also built in. So this is quite unusual, and you don't really see it, which is interesting because obviously the OKHTTP API is completely different to the Jetty API. So, but when you've got this kind of symmetrical behavior, it turns out you can actually do quite a lot of cool stuff. So, testing. Because HTTP applications are just functions, you can test them completely in memory with no network, which makes them really fast to test. It makes it really easy to test. You don't have to start up a server and get a port clash, all this kind of stuff, and you have to resort to trickery like random port selections and all this kind of stuff. So once again, since the building blocks are functions, you can call it without, you can just test it without any infrastructure as well. So we're defining our handler here, and here's the test for it in JUnit. We can say here's a request, and here's the expected response we're going to get. And we can just do an assert, put the request into the function, and we get back the expected response. And because the request and response objects, once again, are immutable data objects, they come basically with completely free equality. So that means you don't need to do any trickery in order to constructing requests and responses is really, really simple. And the other thing you can do is, because you can actually reuse, this is a contract for how an echo server will work. So that's great for running a test in memory, okay? But what if I had a server and I wanted to test that this same contract actually on a real server? Well, because of the symmetrical handler, you can basically just replace the echo functionality, the echo HTTP handler, which was the actual implementation, with a client. And using a filter there, which is set filter from, so that kind of sets the path on this guy. That exact same contract is usable in multiple different scenarios. It's usable both as a unit test and as a system test. And so you get this kind of level of reusability that's really, really useful. So one other thing we want to do, that we had in utterly idle we didn't want to lose was type safety. So when you're talking about HTTP contracts, you might have some values coming in query parameters or in the path or in the body. And we want to be able to kind of draw that into our code without actually manually having to go and get it from the and kind of manipulate the types. And so one of the things that utterly idle did was actually it did that manipulation for us. So you could define things as ints or booleans, and they would get automatically converted. So, for example, here's a way you could do it manually. So basically, this is a Bitcoin miner, which is obviously guaranteed to get more money out than you put in, obviously. And so you can see here that we're basically a URL pattern, mine BTC, and this is basically BTC as a path variable. When you post to this, it's going to take out the BTC parameter out of the path. This is a double bang, which is basically to say if it's null, blow up. And this converts it to int, add 1, and then we put it back into some bit of JSON, and we return it as a response. Now, so there are several problems with this. So the first problem is what happens if the path parameter isn't there? The second is that what happens if the path parameter isn't an int? What happens if I put a string in there? It'll blow up. And then also what happens if not what happens if, but the response here, we're manually creating JSON, which is not exactly the best thing to be doing if we want to kind of reuse stuff. We want to get some type safety in this. So what does that mean? What it means is we want to enforce our HTTP contracts, and that means we want to take things out of the request and put them back into response in a type safe way where we don't have to worry about validation. So what are we worried about? We're worried about queries, headers, form parameters. We're worried about other types of body. And we're also worried about optionality, so things might or might not be there. So that is legal in a situation because not everything is mandatory. And then we're also worried about actually marshalling those types from the representation, which is generally a string in the HTTP message, and we want to actually get the proper object kind of type out. And what about creating outbound messages? We want to do the same thing again. We want to take kind of domain types and try and marshal them into outbound messages as well. So there's a concept in Haskell called a lens we can use to do this. And this is the definition. Lenses and their cousins are a way of declaring how to focus deeply into a complex structure. They form a combinated library with sensible general behavior for things like composition, failure, multiplicity, transformation, and representation. So it's really simple, obviously. So it's so obvious. So in Haskell terms, this is the learning curve of Haskell concepts. I don't know if anyone knows what minor transformer, they're pretty tricky, but lens, apparently, it kind of takes lives when you attempt to learn it. So generally speaking, it's got a bad rap for being very understandable. But let's try again. We can make it simpler. So what is a lens? A lens basically targets a specific part of a complex object to get or set a value out of it. That's all it does. So what is it? It's a function, or actually more, it's actually two functions. Those two functions, one of them is called extract, and one of them is called inject. And extract basically will take an HTTP message, given a lens and an HTTP message, you can extract out a value out of that lens of type X out of the message. That's it. And the inject method, which is the reverse, which is basically taking an HTTP message and a value of type X, and it will return you back an HTTP message with that value injected into it, regardless of where it is, the path or whatever. Now, the most important one thing here is because in HTTP, HTTP messages are immutable, you'll get back a copy after the injection. So, and both these things are actually modeled as invoke methods, which is kind of it's similar to apply in Java. So how does that look? So if we revisit the other example, we've got the Bitcoin miner with all its associated problems. So what we can do, let's introduce domain type, right? So that's going to wrap our int into the response object, and we're also going to move out we're adding a value to the one here. What we can do, we're using operator overloading, which is a feature of Kotlin, and which allows you to replicate this plus operation. We can take the value, and then we've extracted away the concept of adding two BTCs together And once again, this returns a new object because we're immutable. So when you add two BTCs together, you get another result type back. And then there's a toString, basically, which is just taking the value and putting it into a string. So that takes kind of care of the response thing. So, and then we can create some lenses to automatically marshal the types in and out. So the way you, for instance, so there are two lenses here. There's one which is a path lens, and the path lens is to do with taking that BTC value out of the path. So we can say path.int, which is basically saying I've got a path lens, it's going to be an int, and I'm basically going to map it to the constructor of that data class. So that's basically going to take the int and marshal it into a BTC object, and we're going to say it's called BTC. So in the path, you need to look for something called BTC in that pattern that's appearing here. And the second one, which is to do with the body, is going to basically marshal the body object back into JSON. So this is using some Jackson auto marshalling. We can basically take this object, and it will. You can see here, value is obviously the same name as the field. So when you marshal this into JSON, and not only will it set it will construct this exact bit of JSON, but as a bonus, it will also set the content type on the way out as well. So these are the two lenses, and how does it look when we apply them? Oh, okay. Yes. Okay. So once again, we've said here's the diversity lenses at the top, and then here's how a miner would look. So we've basically said we can use the BTC lens to extract out the BTC out of the path. Then we can add another domain value of 1 BTC to it, and we get back the new total, and then we can basically put that, using the body lens, we can put that back into the response and return it. So you can see we had a new response here, and we're basically returning the value, the response with the body injected back into it. So what the most important thing here is that if any of this doesn't work in terms of the types, it will blow up basically, and that's what this catch lens failure filter is for. The catch lens failure will actually catch the error and return a 400 saying you've actually given me a BTC that was a string, or it wasn't there, etc., etc. So this type of lens is actually available for all various bits of the message. So you can do headers and bodies and forms and auto marshalling using JSON objects and everything. So it's all the API is very consistent. You don't need to write any validation code here, which is another thing. So the validation code is basically replaced by the type safety that we've got with the lenses, which should hopefully kind of means you can really just get on with using domain types inside your code instead of doing validation. So how do we use, that said, so that's kind of server as a function, and that's HTTP. That's kind of pretty much how it works. How do we use that inside Oscar? So Oscar itself is about 20 or 30 microservices. As I said, it was Java, it's now Kotlin. And this is how we model our applications. So what we have is normally when you're talking, say, you have a root, which will be an endpoint or a handler, you call them, and that might talk to another service. So we generally wrap a remote HTTP client inside a business abstraction, which gives us the kind of domain level functionality that we want from that service. So given that, we might have a load of routes, basically, and all those routes together, they are individually HTTP handlers, and we can combine them together using the routing to make another HTTP handler. So when we do that, we get an application. So you can see here, once again, we have the business abstractions, which are the services we're talking to. We have the little green blobs are the HTTP clients, which are HTTP handlers. The routes are HTTP handlers, and when we combine the routes together, that is also an HTTP handler. So the interface to calling this application is exactly the same as calling an individual handler itself. So that's great. So once you've got an application, but that's kind of the business level functionality of an application. But we also want to put other things. So we created a thing called an application stack. So the application stack basically consists of things that you need to run your service. So you need logging, you need metrics, you might want to do security, all that stuff, which is actually, very critical to your application, but it's not actually required for mining a Bitcoin. It's just some ancillary stuff that the server needs to do. So what we can do is actually using the filtering combinations, using the composability of the filters, we can actually add all those filters together. So that logging will be a filter, metrics will be a filter. So we build these like stacks of filters, and then we apply them to the application. And what do we get? We get another HTTP handler. So the interface to the application is the same as the interface to the root, which is the same as the interface to the application stack. It's still the same thing. It's just been decorated with some more functionality. And the last thing we want to do is we actually want to launch that onto the network. So this is the you need to load some configuration. If we're doing like 12-factor applications, then we'll load some configuration from the internet. So we need to know where we're going to talk to our remote dependencies, and we need to launch that thing onto the network. So that's kind of where we would, in this outer layer, this is where the actual server launching happens. But everything else is completely testable. So the launcher will end up with a thread running, and it will that's kind of your main, as it were, the main in a program. But everything else is the same functionality or the same interface. So these standardized service and filter stacks that we created, because we can use filter.then to compose these things together, we can create standardized stacks of behavior. So this one is doing logging transactions, and it's recording some metrics, and then handling some errors, and only then we're wrapping in the app there is our actual application, our core business logic application. And we can do the same with the clients as well. So we want to also see how our clients are behaving. We want to be able to put metrics and all that good stuff. So what this gives you is a reusable way of creating identical stacks across your entire microservice estate. So dependencies. So as we came to saying, well, we can model all of our stuff using basically the same interface, we started to say, well, what do we do about dependencies? So our dependencies are HTTP servers mostly, and so normally we could actually when we're mocking out behavior of our dependencies, we could mock out that our business abstraction, but then we're actually losing how that business abstraction actually behaves. What we really want to do is actually mock the kind of transport layer, basically. So what we decided to do is actually create fake versions of our dependencies that are all HTTP, and they are all also HTTP handlers. So we can leverage all the same stuff, like the body lenses and all that kind of that composability to actually create simple fake servers that return things we want. And we can also use this to model what happens if things time out or if things throw a 500. How does your business abstraction behave if there's a 403 from a downstream server? If you mock out the business abstraction, you'll never know exactly how your business abstraction behaves, because that's the thing you're actually trying to test. So what we did basically, these fakes that we were creating, they're basically some simple a little state machine, some lenses, and another HTTP kind of routing block that actually mimics the API. And this turns out that when you do this, you can actually, when you have a similar state for loads of applications, you can plug them all together because the interface is symmetrical between client and server. It means that in place of a remote client, when you actually want to write a test, you can just inject the other system. You don't actually need to do anything over the network at all. So we ended up testing. We ended up testing in a monorepo all the entire. If we wanted to write an end-to-end test, we could just take all our systems and basically plug them into each other, and all in memory. So it's already fast. It makes it just simple. It was very, very simple to do, and it actually really leveraged. We can run all the tests really quickly, run them all in parallel. It's all pretty good. So the other thing is, of course, that there is no spin-up time if you do everything in memory. So that's why it's very fast. And then in a test, we could take this this thing, and we load some environmental configuration, and you don't actually have to. What you could do is actually you could take 5 of these. You could take 4 of these services, and actually for one of them you could actually configure it to actually talk to a real server, or you could take 4 real ones, or any number of these can be basically completely fake, which is what we did. We can just take the fakes that were created and inject those instead of the actual real applications that we've created, and that will allow us to actually see what happens when they fail. And that's a thing that's really important, to be able to kind of, how does my system behave when this downstream system is taking 5 seconds to respond? It allows you to answer these questions really easily without actually having to spin up complicated like Docker containers or whatever. It's all kind of in there. So it's all very well having these fake APIs, but how do we know they act as if the real API does? So that's where a thing called consumer-driven contracts come in. So consumer-driven contracts is basically a way of saying, here's a contract, I want to make sure as a consumer of this service that my fake behaves the same as the real thing. So what you can do is you can say, you can construct an abstract test contract with some known scenarios that will work. Here's a business abstraction. We're always going to test through the business abstraction, and then we have a client here. Now, what you can do is actually implement this thing twice. So we implement a fake one using our fake that we've created, and we also have one that talks to the real system, the real test system, if one is available. That means that because the contract is defined here, we know that both of these tests, if they pass, this business abstraction is for these set of scenarios acting as if it was the real thing. The other thing is that obviously with real dependencies, it's difficult to make. If you've got a downstream system, how do you make, what happens if it blows up? It's unlikely that downstream systems are going to tell you or give you an API that say, this is what happened when we blow up. So you can actually increase your coverage by actually adding failure scenarios into the fake, and then you can test how your business abstraction behaves under failure scenarios. So these all run as part of the build. Because this is like a unit test, it can just run really fast. This is obviously a kind of more of an integration test, external test. So performance, kind of a bit of a side note really. So we always get asked, like, how does it perform? It doesn't really do anything. You've got this immutability, but how does it perform? So we entered HttpHandler into the Tech Empower benchmarks, which is it's kind of a suite of over 150 different frameworks and libraries. They put it under various loads, starting at not very many clients and ramping up. It does real world scenarios like talking to a database and like marshalling some JSON or templating some HTML to go back. It turns out that HttpHandler is pretty good in terms of I think we're 11th overall, and in terms of the just if you narrow it down to just JVM, we were, I think, 7th in the entire out of everything. So including all the ones, Spring, GB, whatever. We were number 7. To our surprise, the Apache server turned out to be the most performant, which was kind of doubly amusing because we didn't even implement that. That was implemented by a contributor to the GitHub repo. So that was a nice surprise. So it's interesting that we didn't do any tuning either. It doesn't do no clever tricks. I think we played with like the memory size and the garbage collector, but that was it. There's no fancy stuff to get that performance at all. Okay. So what did we gain? So we gained pure Kotlin services. We gained no magic. So the lack of magic annotations means that it's basically really easy to test. It's really easy to work out what's going on. Because it's immutable, you can actually just step exactly through and see exactly what every value is at every single point in your stack. Less boilerplate, which is all great. Everything's in memory, so the tests run really fast. And that's really good as well. And so we've discovered that actually the end-to-end testing becomes really simple as well. And that's good. Here's a quick demo. So we obviously can't share the Oscar code base, so we kind of come up with a demo. It's a video because I'm not brave enough to do it actually on the real thing. That'd be foolish. I've seen that go wrong too many times. So what do we build? We built basically it's basically a Dropbox clone, basically allows you to basically a website that is backed by an S3 bucket, and you can upload files, and it'll put them in an S3 bucket, basically, and it's got some security on it. So this is available on Heroku. It's running on a single dyno. It's got some security. Basic security is applied by filter, so that's all good. And this is the application. You can basically just upload a file using a WYSI thing we found on the internet, and then you can basically delete or view the files. So that's pretty simple, but it does kind of do quite a lot of functionality. So it's quite nice. And so the nicest thing about that, though, is that entire thing was less than 70 lines of code. That's the power Kotlin gives you. And 70 lines of code is less than that one class was at the start within Java. So we're using basically the core. There's a web service. We have a thing that does AWS request signing, some handlebars for templates, and the Apache HTTP server, and it's running in Heroku. It's here if anyone wants to play with it. That's the auth is this and BrizTech. Please don't upload gigs and gigs to my S3 account because I have to pay for it. Yeah, so that's kind of I suppose that's almost it. I'm gonna run out of time, so what I'm gonna do is actually zip over another couple of things that we did. We started looking at deployment modes, and we said, what can we do? Do we need to actually run stuff as a server? Because we've just got a function. So what can we do? So it turns out we can put things into Apache AWS Lambda. So without any, basically you can test your HTTP applications, HTTP4K applications. You can wrap them in a really simple function, and you can, with a bit of jiggery pokery, you can actually plug them into API Gateway and put them onto the network, onto AWS. And because it's simple request response, it's really easy to do. Also, ProGuard, you can get the binary size down to really, really small amounts because dependencies, with larger frameworks, you find that the actual, somebody did some research on the internet and found out that the number of dependencies, as the number of dependencies goes up, that has a really bad effect on your loading time for your Lambda. So the cold starts kind of really start to bite. So we can end up with really small binaries, which is great. Native for K as well. So there's a thing called GraalVM, which is basically a polyglot framework for packaging applications into native binaries that can run really fast, basically. So that's quite it's a new thing. It's pretty it is quite early days, but it's been really promising in terms of being able to get really, really, really fast, really fast kind of startup times. So that's cool. And here's just one word about the ecosystem, basically, which is basically these are the modules we've got. So HTTP core, HTTP4K core is basically 800K. It's got no dependencies. It comes with a Sun Apache client, a Sun client, and a Sun server. So if you want to throw together a development server, you can basically do it with just one dependency and Kotlin. That's it. We support various back-end services. So that's these are the front ends we support. So sorry, not the front ends. These are the clients we support. And there's some libraries like Jackson, JSON for doing formats and stuff. Templating libraries. Testing is very important to us. So there are things like there's a WebDriver implementation. There's some Hamcrest matches, which is like a testing thing. And there's like Chaos Monkey, which allows you to do chaos testing, which is really good. And there's also web services modules and some open API stuff, so you can generate Swagger docs as well. I'm not going to go through that because of time. Thank you very much.